Hello ICSE 2021. I'm Jared Rand, and today I'm presenting work that I completed with Dr. Andrew Moransky. We're from Ryerson University, Canada, and today we'd like to present to you our research on automatic log parsing using machine learning. Modern software solutions consist of hardware and software components. Failure of a component may lead to an outage, so it is crucial to be able to quickly detect failures and identify potential root causes. Finding root causes is a heart attack-inducing and time-consuming problem, taking up to 40% of the time needed to fix the problem. Finding the root cause of a failure can be done by examining the logs emitted by a component. These logs can also be used to detect cyber attacks or audit policy compliance. Tools for automatic log examinations already exist, yet prefer the logs to be in a single, unified format. However, since a software solution may consist of multiple, even thousands of components, potentially each with their own unique log format, using these solutions requires unifying the log formats, which could be a daunting task. There exist methods which are based on detecting the field type in a record set or comparing multiple log strings, but for our paper, we wanted to see if we could individually parse a complete raw log string without comparing it to other log records emitted by the same component. Thus, our task was to create an oracle using machine translation that, given a raw log string, would produce a string of tokens showing which log field a character belongs to. Currently, the best models for machine translation are based on deep neural networks following an encoder-decoder architecture that implements sequence-to-sequence learning. We chose to create our models using LSTM cells instead of GRU cells, as LSTM cells outperform GRUs in preliminary tasks. We created three architectures. The first using a classical machine translation architecture, the second adding an attention layer as per Badenow et al., and the third based on a sequence-to-sequence architecture with a Luong et al. Attention mechanism. With our models ready to go, we encountered the question of how to train a model to take raw log as input and output a character to corresponding field mapping. Let's take a closer look at the problem before delving deeper into the inputs we used. Here, we see an example of the model input and desired output. On the top, we have a sample log string, and on the bottom we see its one-to-one character-to-field mapping. In our case, we chose to focus our efforts on decoding Apache HTTP server logs. Apache HTTP logs can contain up to 42 different fields, but most use one of two formats presented here. Common log format, or CLF, which only contains 7 of the 42 fields, and combined log format, or ELF, which extends CLF by 2 fields. In order to train these models, we needed a large amount of sample logs along with their corresponding character-to-field mappings, as discussed in the last slide. While there exist tools to generate synthetic Apache logs, they do not output these sorts of character-to-field mappings, and trying to automate creation of these mappings is essentially what this entire presentation is about. Additionally, most of these log generators we encountered only output logs in CLF or ELF formats, creating a problem for generalization. Thus, we set out to create our own fake Apache log generator. While a real Apache HTTP server can generate 42 fields, our generator can only create 15. However, the tool is easily extendable. It allows the user to specify the total number of log records to produce and provides hyperparameters to tune how often logs should appear in CLF, ELF, or completely random formats. We see here an example of logs in CLF, ELF, and random formats respectively, generated by the tool along with their corresponding mappings. To validate the generalizability of our models, we also retrieved 3 publicly available log files and parsed them to create corresponding mappings. In addition to the 3 real log sets found online, we generated 4 groups of synthetic datasets to train the models on. We organized these datasets by difficulty for the model to learn. Datasets that more often contain logs close to those in the validation set are considered easier, while datasets that contain fewer matching logs are considered harder. The first one was trivial for the models to learn, consisting only of 100,000 mock logs in ELF format. Models trained on this should be able to recognize the ELF format well, yet should not be very generalizable to other formats. Since the validation datasets are entirely in ELF, models trained on this should perform very well. The second one was easy for the models to learn, consisting of 20,000 lines in a mix of CLF, ELF, and random formats. The third was moderate to learn. It consisted of 100,000 lines, approximately 50% of which were CLF, and the rest were random formats. This group would make it harder for the model to recognize ELF, as it would have to learn the two fields not present in CLF exclusively from their usage in random formats. We also created a shorter version of this moderate dataset that we call moderate prime, consisting of 20,000 lines instead of 100,000. The fourth group was hard, consisting of 100,000 logs in random formats, none of which looked like CLF or ELF. To test the generalizability of our approach, we created 3 groups of experiments where a model is trained on one of the training datasets mentioned in the previous slide. For details about the hyperparameters used, please refer to our paper. We evaluated the performance of the models using 3 publicly available datasets mentioned earlier. We used the edit distance to measure the performance of the models, calculating the absolute and relative Levenshtein distances of each log such that the closer the edit distance is to 0, the better. An important point of consideration while comparing the models against one another is by aggregating their performance on a real-world validation dataset. Over here on the left, we can see an example of the distributions of the absolute edit distances for a model trained on a moderate dataset. We can observe a long right tail. While the median lies between 51 and 61, the maximum edit distance clocks in at a mere 4,283 due to a few exceedingly long records. Once the results are normalized using an edit distance relative to their length, we observe that the number of changes are proportional to the string's length, with the median being between 21 and 25%. I recognize that there are a lot of scary looking numbers in this slide, so we'll just do this for now. We aggregated summary statistics for the best performing models in this extremely intimidating table. The D character represents the dropout rate used in the model. The models with the attention mechanisms underperformed and thus are not shown in this table. Recalling the difference in size between the moderate and smaller moderate prime datasets, we observed that a larger dataset improves the performances of the model. However, we observed diminishing returns as increasing the dataset size by a factor of 5 led to only incremental improvements. Moreover, we found that the model trained on the shorter easy dataset outperformed the model trained on the longer moderate dataset. This implies that the quality of the input matters much more than the quantity. As expected, the performance of the model degrades as the difficulty of the training dataset increases. The model trained on the trivial dataset performed the best on the real log validation, as it only needed to learn the fields beginning and ends while the order stayed the same. The model trained on hard data performed the worst. Not only did the model have to understand the beginnings and ends of the fields, but also had to learn the field's order whilst never having seen an example of ELF before. To our surprise, the model trained on the hard dataset did not fall behind the others significantly in performance and was quite close to the moderate model, with the median relative edit distance between 0.25 and 0.28, and the 90th quantile of relative edit distance between 0.26 and 0.43. This implies that the model trained on the hard dataset was able to learn the concept of fields relatively well. To answer a research question, we reformulated log parsing as a machine translation task and explored 3 machine translation architectures. We showed that models based on an LSTM architecture were the most promising. Moreover, the model trained on randomly generated log records was able to partially parse log records in a format that it had not witnessed before during training, implying that parsing individual strings with machine translation is possible. This work provides novel insights into the log parsing fields. While the quality of our models is not adequate for use in real-world tasks yet, we hope that this work will inspire others to explore using machine translation approaches and improve upon our results. To aid these researchers, we created a tool for generating synthetic logs in the Apache format that we use to gather training data for our models. We have made this tool publicly available on both Zenodo and GitHub and are accepting contributions to further advance the tool. Thank you for listening to our presentation. For further details, please read our paper.
Welcome to the question and answer session of the paper on automatic parsing of log records. Andriy Miransky from Ryerson University has joined for this session. I would like to thank also Jared Rand for the video we have just watched. And please make your questions in the chat and he will be glad to answer. Let me start with first question. So you focus on Apache server logs. About generalization, for what other logs could your approach work?
Hypothetically, for any logs, right? So this paper was kind of an empirical study to understand, are the machine learning models generalizable enough to pick the specificities of the format, and it seems they can, and Apache format in itself is relatively complex. So this implies that probably other formats would be able to be picked up and learned as well.
Very good. We have many questions coming up. First one is from Georgios Josios. How representative are the synthetic logs of actual application logs?
So we used the Faker library, and some of the fields are very representative. Some others, especially the ones that mimic the post and things like that, we deliberately made things fairly weird. So say the names of the websites were generated in random, so you will see some random string there. And yet the system was still able to pick up the cues and kind of try to understand what's going on.
Okay, another question from Henry. Interesting work. How do you get the labels for the evaluation of real datasets?
So we ended up, because we knew the format in advance, so we wrote the parser ourselves, and we created a couple of Python scripts that took the original raw logs and produced the labels. And the scripts are available through the GitHub and Zenodo. Like, there are links in the paper, so you can readily reuse them if needed.
Another question from Jasmine Latendres. Can you tell us more on the extensibility of the parser?
Extensibility of the parser? Well, I think it's extendable, right? So fundamentally, it's a machine learning model, right? So if we feed in a different type of data, it will learn from that data. So we can feed in different types of log formats. We can build better parsers, right? The one that we have is relatively naive. It's a basic LSTM, and it works. But I'm sure that kind of better models can be built to make it smarter. So kind of there's at least two avenues here, and I'm sure that you can probably think of other and better ways.
Great. Another question from Henry. Which log fields did you consider, like timestamps, lever, or any other?
So there are, let me just see, I think there are 15. Yeah, I won't be able to count quickly, but I think it's around 15 fields that we generated, timestamps including. And they're kind of the most common ones. And in principle, the tool that generates synthetic logs, you can add the fields to it and extend it, because the whole Apache system, I think, allows for up to 40 fields, and we just didn't have time to implement them all, especially given that our validation one had only, I think it's 9 fields, right, the common format. So we just try to make it larger then and see what happens.
Okay. Thank you, Andrew, for your answers. Also for the audience for all the questions. We have less than half a minute to finish this session. I would like just to remind that you could go to the join the discussion room and talk with Andrew and reply to their questions like how the tool could be extended and so on. So thank you, everyone. And this closes.
Thank you very much for the questions.
Thank you. Bye.